Okay, it's been requested that I talk about God and math a little bit, okay? So we need to talk about sets. A set is just going to be a bag of stuff. The specific properties that make a set instead of like a conglomerate or something else don't really concern us here because all of the relevant properties generalize, okay? So we have a set bag of stuff. We have another bag of stuff. We can talk about functions between them. So if we have a function here that maps this one to this one, this one to this one, this one to this one, then it is called injective. It's injective because every one of these gets its own partner. They don't share. So if this one and this one were to both go to this one, then it would not be injective. Now, as it stands, this function is not what's called surjective. To be surjective, everybody over here has to have a partner over here. But we don't have that. But we can make it that way. All we have to do to make it that way is not talk about this whole set. We don't want to talk about all this. We just want to talk about this right here. And so this, the set of all the things that are actually being mapped to and nothing extra, is called the image of the function. So if you have a function between a set and the image of the function, then that will be surjective every time, just because by definition what the injection is, by definition what the surjection is, and definition of what the image is. Right? So if it's both injective and surjective, then it is bijective. And if you have sets that are bijective, then they have the same number of things, which makes sense, right? So if you go this way, and then you can go back because they each have partners, right? That's a way to prove bijection, by the way, is to prove that you can go back and forth. Yeah, so they will always have the same number if they're bijective. Okay, so sets also have a nice little fun fact where every set that exists has a friend. So for any set S, we have its power set. Now, if set S is triangle, circle, square, then the power set is going to be the collection of all subsets of S. So what we do is we go and pick out any subcollection of S. So one way to do that is we pick out nothing. So nothing gets in there automatically. And then we're like, hey, triangle is a thing. So the set of just triangle. And then similarly, the set of just circle. The set of just square. The set of triangle circle. The set of triangle square. The set of circle square. And the set of triangle circle square. Now, if you've noticed, there are 8 subsets here. And there are 3 things in the original set. So for any set with n members, its power set will be 2 to the n members. And that's why it's called a power set. Now, this is for finite sets. For infinite sets, the power set is the next biggest kind of infinity. Okay. So, yeah. So, we have something called Cantor's theorem that talks about that. So the size of the power set is always bigger than the size of the set that generates it. So we have a couple of facts that we were going to make a point of. One, if S exists, then the power set exists. 2. The size of the power set is always bigger than the size of the set that generates it. 3, if there's a bijection that connects them, then they have the same number. And 4, restricting the codomain, which is any set that contains all the things that being mapped to the image, is going to give us surjection. All right. So what we need to do here is show that there has to be something that God doesn't know. And then we have shown that omniscience is not the case. Because omniscience, as historically, currently, and even in the popular usage, is God knows all and only truths. So if it's true, God knows it. If it's false, God doesn't know it. Right? Okay, so we're going to just slap a label on the set of what God knows. Call it K. So then we're going to take the power set, which is bigger. We know that from Cantor's theorem. The problem here, the reason why we're not done at this step, is that this is made of truths, and this is made out of subsets of this. So this is made of sets, this is made of truths. They're different kind of things. So what we want to do is make a function that finds truths and then look at its image. All right. So by going through each member of the power set, we guarantee injection. By restricting to the image, we guarantee surjection. So we have this image set will be the same size as the power set, but since this function finds truths, instead of being made out of subsets like this is, it's made out of truths. All right, so what is F? How do we get there? So what we're going to do is just ask a question. For each member in here, we ask, is it a subset of K? And by definition of PK, of the power set, the answer is always going to be yes. So then for all X in the power set of K, we're going to say that X is a subset of K. And so by definition, the statement will always be true. And this is what we're going to do. We're just going to go dot by dot through this and make a truth by saying that this is in here. And that is, in effect, extensionally equivalent to asking, does God know what God knows? Okay. So this image here is made up of things like this. So now we have a set that is bijective to PK. So, since it's bijective, we know that its size is equal to the size of PK. But we also know that this has to be bigger than K, right? And since these are the same size, then we know that there are more truths in this set than there are in K. So there have to be truths in here that are not in here. So there exists a truth not within God's knowledge. So then K is not the set of all truths, so God doesn't know all truths. It's really that easy. And I said that it generalizes, right? So it generalizes pretty hardcore, actually. Because we can talk about something called a topos, which is got several definitions and useful in several areas. But the one we want to talk about here is a topos is a thing that has logic. So if we can generalize these facts to be about any kind of topos instead of just sets, then it's not only logically impossible for omniscience to exist, it's metalogically impossible. So there's no kind of logic in which it'll work. Well, no kind of consistent logic anyway. All right. So what do we need? We need that for any object, let's call it O since we're talking objects instead of sets, that its power object exists. And that is provable from the fact that exponentials exist in the as like part of what requirements to be a topos. Alrighty, and then we need Lauver's fixed point theorem. And that is just a generalization to toposes of the Cantor's theorem. So that just says that, well, it's a corollary of this, that the power object of any object is bigger than the object itself. Alrighty, so let's see. We've got, yeah, that's all we need. Alright. So if there is logic, then there's no omniscience. And this is not just about Boolean logic. This is any consistent logic. So intuitionistic logics. You can't even give up the law of excluded middle to try to get your way out of this. It's just that, like, good of a generalization.